Great, it's wonderful to be here. It's my first time in Singapore, and thank you for inviting me. The talk has really two parts. I'm going to spend a little bit of time, since I've been at Microsoft almost 20 years this August, and you're celebrating 20 years, I thought I would introduce why we're doing formal methods and tools for distributed systems by looking back over 20 years. And then mainly I want to talk about those formal tools, which is the great work of many others at Microsoft. Today, I'm working actually on something called Make Code, which is a programming platform for CS education. So while I manage a lot of work around formal methods and tools, I'm not engaged day to day, but I'll be talking about that. So 20 years at Microsoft, I wanted to sum it up with sort of 4 themes that help explain the title of the talk. There maybe be a little mysterious. From EULA to SLA is the first theme. From bugs and bounties to cyber weapons is the second theme. From spec to spec and check, from specification to specification and checking, and then from closed to open. So these might be mysterious to you, but each of these 4 themes I hope will become clear in time, and they're all sort of interrelated. Okay, so from EULA to SLA, how did Microsoft make its start? How did we make money back in the 20th century? Does anybody recall what we did there? Well, we made software, and if you go out to the History Little Museum, you'll see these disks, so I put a disk there. And the great thing about software is it's really easy to copy, and if you remember Bill Gates' original vision for Microsoft was a PC on every desk, and Microsoft created the software for that. And the interesting thing about this endeavor was that it was primarily human intensive, right? The programmers create the bits. Once you've created the bits, copying them and distributing them is actually pretty cheap. But really what this did was it made everybody into a system administrator, right? So if we think about the cloud, like a PC on every desk really meant that everybody had their own little personal cloud at home, right? Where they had to think about, oh, what's the speed of my computer? How much storage does I have? Is it networked to my other computers? Have I done a backup lately? And if you worked for Microsoft, you would often go to somebody's home and they would say, can you help me with my PC? Because of this. So really, a PC on every desk really meant a cloud in every home. That's sort of a little cloud, right? And what was the recourse if people had problems with the software? Well, there was this beautiful thing called the EULA. Does anyone know what a EULA stands for? Okay. Sorry? End user license agreement. Right, so this was amazing. And I actually, when I was talking about formal methods back in the early 2000s, I would use this as an example of an amazing form of behavioral, like what would we say about the behavior of software? And as a contract, as a formal contract, but you could go to a EULA and you could read, for example, in the Microsoft PowerPoint EULA point 11, in no event shall Microsoft or its suppliers be liable for any special, incidental, indirect, or consequential damages whatsoever, skip over the green stuff, arising out of or in any way related to the use or inability to use the software product. So whatever this bunch of bits does or doesn't do, it's up to you. And it wasn't just Microsoft and closed source, right? Look at the GPL, right? The entire risk as to the quality and performance of the program is with you. In no event will any copyright holder or any other party who may modify or redistribute, blah, 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 be liable to you for damages arising out of the use or inability to use the program. And from a viewpoint of somebody trying to get formal methods going at Microsoft, this is like, wow. This is pretty amazing, right? And so in some sense, you had this proliferation of programs, and then the behavior was, and the risk of using that was up to the system administrator at the edge, the PC owner in the cloud at home. Okay, so I think it's rather rich when you think about now Microsoft's business model is a hybrid model. We still do sell software the old way, but if you haven't been paying attention, we've transitioned and in some sense take all those PCs and glom them together and distribute them in data centers around the world, and Microsoft now owns a really big distributed computing system. Sure, there's still the PCs out on the edge, but Microsoft has transitioned now from really being a pure software provider to owning a huge supercomputer called Azure, which is a huge number of data centers around the world linked together in networks. And we take care of the compute, the storage, the networking, the backups, the system administration. So it's, if you think about it, it's completely inverted sort of the business model in a way. And what we want is we're not distributing programs. We want users. We want users who are developers to bring us their programs. We want people who want to do machine learning to bring us their data. And we want users, of course, because as programs and data resides on Azure, well, people should come and use those. And instead of the EULA, you have something called the SLA. Okay, and everybody know what the SLA is? Service level agreement. So just to give you the idea of how big a transition this has been for Microsoft, let's look at the scale of Azure. What does it mean to do cloud scale computing? So Azure currently is 54 regions planned worldwide. I believe there are actually 42. So Microsoft is one of the few companies with the reach to go global, and we've put data centers all over the world. I think 42 geographical regions with a plan to reach 54. And what does a data center look like? Okay, that's the view from the sky, and that little thing in the lower right-hand corner, that's a car. So data centers are huge capital investment. Remember how I said before that primarily when we were just producing software, the major cost was people's salary. But now, billions and billions of dollars are being spent. You have to acquire the real estate, the power, you have to build the thing, you have to operate it, right? And to just give you an idea of what one of those buildings on the left looks like, you can fit 2 737s in it, right? So this is huge, huge supercomputer, and this is just one data center. Remember, there are going to be 54 regions, we said, and each region will have several data centers. So just to give you an idea of the investment, now we really want that data center to be up and available and usable because there's a lot of sunk costs there, right? Furthermore, instead of a EULA, right, which said whatever the software does, we now have an SLA. So here's one example of what an SLA looks like. So for all virtual machines that have 2 or more instances deployed in the same availability set, we guarantee you will have connectivity to at least one of the instances at least 99.95% of the time. And what happens if Azure doesn't meet that level of service, then we essentially give you money back, which is a service credit, right? So now we're running a computer, and if the software goes wrong in some way and becomes less available, if the service becomes less available, we pay out money. So it's a very different, we're in a very different world. So just to give you the idea, Microsoft's business model has really transitioned from just producing software to owning and running a huge global supercomputer, right? And having service level agreements. So that has a huge, huge impact on the way we work and the way we think about the cost of bugs and how we do business. So that's just in case you weren't paying attention to Microsoft. We've really been under transition, and this has been going on now for really almost, when did Azure start? Really in earnest. Red Dog was started maybe 2006, so 12 years now that we've been doing, that we've been starting on the cloud. Okay, so that's the first theme. The second theme is what's happened with bugs over the last 20 years. Because there are so many more ways for things to go wrong than there are for them to go right. I've been reading about entropy lately, and that's why we have bugs. People just make bugs, and I'm sorry, you know, we make them at a constant rate. People introduce errors, but the impact of those errors has increased over time. So when I started at Microsoft, we had something called NIMDA, admin spelled backwards. It really didn't have much to do with admin. It was a bug in the way you handled MIME types, and basically an attacker could send you a piece of email with an attachment that was a forged MIME header saying, I'm an audiophile, and Windows is like, oh, we love audiophiles, we love to play them, but it wasn't really an audiophile, it was just an exe that would do anything arbitrary with your computer. So this is what happened with NIMDA. There was a bug, and it allowed people to just mail you arbitrary content masquerading as sort of something that Windows said was safe, but it wasn't safe, right? And as a result of this, we had there was a worm, and it went around computers. It brought down quite a number of PCs. And as a result of that, in 2002, Bill Gates penned the Trustworthy Computing Memo, and it's worth sort of reading a little bit of it. And he identified availability, security, and privacy as 3 key goals. And we're going to hear more about security and privacy today from Uvar, and I will talk a little bit more. Products should always be available, so this goes to the SLA. This is before we had Azure, but system outages should become a thing of the past. Software architecture supports redundancy and automatic recovery. Security, the data our software and services store should be protected from harm. Privacy, users should be in control of how their data is used. And this was, if you were at Microsoft at this time, something really amazing happened. They stopped doing Windows feature development for almost 3 months, and they got everybody trained on security principles, and they created something called the Security Definition Lifecycle, which exists to this day. And so it grew out of this idea that, well, you had all these home PCs, but now they were being connected by the internet, and there were bugs in the software, and so there were malicious attackers, and we needed to do something about this. So the SDL, and I'll say a little bit more about that later, was to define a process to go through and a set of supporting methodologies and tools that before you would release software, you would go through this to make the software more secure. And there were many things that MSR was involved with as well. So you can read all about this. It's really it's gone on through today. It's a standard there for really dealing with security and the types of bugs that lead to exploits, and trying to create a process and tool to minimize the number of those. Nonetheless, how were things going in open source land? Well, all these eyeballs make bugs shallow. Well, so much for that. In OpenSSL 2016, Cypher suites are susceptible to a denial of service attack by corrupting larger payloads. We can crash it. Here's sample code that produces wrong results for Poly 1305. That's some crypto. These produce wrong results. The first example does so only on 30 bits. This affects various things. Oh, I'm going to generate some random inputs and stress all the other code paths against a reference implementation. So what was all this about? It was about OpenSSL. It was about the underpinnings of the secure internet, HTTPS, like when you connect to make a payment or anything where you want to have cryptography and cryptographic protocols protecting you. It was all just for naught here with this bug, right? So this weakness allowed, under normal conditions, allowed stealing the information protected by encryption. This is the protocols used to secure the internet. So this was also a pretty big wake-up call, right? It turned out that people hadn't really been looking at this code. This code hadn't been going through the SDL clearly, and that was called Heartbleed. So the other thing we've seen over the years is like people pay for bugs. I mean, what's the impact of a bug, the cost of a bug? Well, you can go out there and make money by finding bugs, right? And over the years, you can measure the cost of a bug by what people are willing to pay for bugs, right? So there are these bounty programs that started really in the mid-90s, have grown over time with many companies offering these bug bounties. So bugs really do matter. They matter because the environment's changed, and also because our immune system is always being bombarded by attacks, by viruses. Really, that same thing is happening out in the wild. The internet is open. There are great uses of the internet, but there are also actors who have different motivations. And one of the most incredible examples is something called Stuxnet. Who's heard of Stuxnet? Okay, I hope so. So this was a malicious computer worm first uncovered in 2010, and it targets a type of industrial control system, and they believe that Stuxnet was responsible for causing substantial damage to Iran's nuclear program. So if you haven't read up on it, please do. It's on Wikipedia. The amazing thing from the bug standpoint was this worm used 4 unknown zero-day attacks. The number of zero-day exploits that was used in this worm was really unusual. These are again, if you go look at the bug bounty programs, the cost of each of those would be very high, but there was an organization that had those for and used them. Yeah.
How many would become known in a year?
How many?
0-day exploits.
That's sort of unknowable, isn't it?
Well, I mean, that you eventually come to be aware of things. That it would be that significant.
I don't know. I'm not in the. Maybe Overo can tell us more later, but.
0 days are very rare, rarely found in the wild. A dozen a year.
Okay.
So 4 of them in a single attack is completely unprecedented.
Yeah. Oh, 0-day attack means fundamentally that bug is not known to the security community, right, Tovar? So basically, this is somebody's attacking you with a new weapon you've never seen before, right? Essentially, it's a new attack vector that hasn't been disclosed. Yeah. So this is just to give you the idea. It's a really serious game out there. You have state actors, you have script kiddies. Any system you build that's of any scale will be under attack. And if you have bugs, you can expect that your system will be broken into. It's not a matter of if, it's a matter of when. Okay, well, how about formal methods? How have we been doing in the last 20 years? So I would say it's been a pretty good run, and I wanted to tell you a little bit about formal methods as background. Formal methods, the way I define it, is really a mathematical, logical specification of the desired correct behavior of a system, shown in this big Venn diagram as being in the blue bubble. Let's say that's a set of states or a set of traces. But if we just specify it and we don't have tools, then we're reduced to paper arguments and pushing things around. So we'd also like to have automatic and interactive, perhaps checking of an implementation against the specification. And so we hope that our implementation, in terms of this Venn diagram, its behaviors and set of states is within the specification. Or if we've made a bug, we're not inside. So that's formal methods in a Venn diagram at a very high level. Back in the States, we'd always start math every year with, here's what a set is, and here's where a Venn diagram is. So I always like to draw them. But it gets a little more serious than this. So but at a high level, this is what formal methods is. What do we mean by a specification? Well, if you look at Heartbleed, that was a buffer overrun. So we'd like our code, if it's C programs, not to have buffer overruns, or for it to be memory safe. That is, when I use an integer, it's always an integer and not something else like a string. Or I'd like functional correctness, please. I like my sorting function to really sort. Or I'd like to know that this function terminates, or terminates within an expected amount of time, worst case execution time analysis. If I'm thinking about privacy and securities, I'd like to minimize side channel leaks or cryptographic security. So there are many things that you might think of as non-functional properties, but we can also reason about them formally. And the list really goes on because in some sense the set of behaviors that might be under attack or might grow. So the specification that is good this year in a couple of years might be outdated by some new attack. Now, what do we have to say then if we have a system and a property? So now the property is my specification, and my system S, that's my implementation. And so I would like to do verification and either get a proof that my system satisfies the property I have in mind or violates it, in which case I get a counterexample, like some test that shows me that system S is not memory safe. Well, there's this Rice's theorem that basically says for any reasonable property you want to ask of a program, it's undecidable, right? And so for many years, this has sort of been the idea. Well, formal methods, yeah, it's the future. It's the future. Always has been, always will be. But I would like to say we've made a little progress, and we've known for well over really since von Neumann and then Floyd and Hoare, how to do what's called deductive verification. So how many people know about inductive invariance? Okay, okay, good. So I'll do a little review. So the way we're going to prove that a system S satisfies some property is we're going to make an inductive argument the same way we're going to argue the same way we're going to argue some mathematical property. inductively. And so we're going to have to come up with some inductive argument, and then verification is the process of saying, does this inductive invariant that I can prove for S, is it strong enough to entail or imply the safety property? And when I do that, I might get a proof, I might get a counterexample, or I might just I might not know because of undecidability. So here's the idea of inductive invariance. The bad states, the states that I don't want to reach, like buffer overruns, are the red ones, and the safe set of states are all the rest outside of that red bubble. Now, I start my system off in an initial state. I start executing at main, and I take steps in my program. And if my program is safe, then the set of reachable states, the blue area, doesn't intersect with the red. Okay, and that's my idea of a safe program, but that's not a proof, right? What characterizes the set of reachable states? Well, that's pretty hard to know. So inductive invariance to the rescue. An inductive invariant is some set of states that contains all the reachable states and doesn't intersect with the bad states. It's an over-approximation, so it encloses the reachable states. And it basically allows us to get a handle on how to do proof by induction of the safety of system S. So essentially, the inductive invariant, the green part, has to satisfy three equations. Initiation means that the set of initial states, remember those initial states there, they have to be inside the inductive invariant. So we have a base case, okay? So think of that as the base case. The induction step basically says that that inductive invariant is closed under taking a step in the program. So if I have a state, a sigma, that's in my set, and I take a state, and I take a step from sigma to sigma prime, then sigma prime is also in my inductive invariant. So it's closed, okay? And so what those two things mean is that the inductive invariant contains all the reachable states, right? And it may contain other states, but if I take a step under the transition relation, under a step of the program, I'll never go outside, right? So it's closed. And furthermore, the third property is that set of states, the inductive invariant, doesn't intersect with the bad states. So getting a precise handle on the reachable states might be very hard. So the idea is to find an inductive invariant that I can prove by induction covers all the reachable states, yet doesn't intersect with the bad states. Okay, so that's the scheme we've been using for many, many years, for over half a century. And the idea is to use logic and represent these sets of states, the initial states, the bad states, the inductive invariant, as well as the transition relation by logical formulas. So a formula is really something like x less than 5, like all states in which the integer variable x is less than 5, that's a set of states, that's a bubble, right? And then we can reason about these questions of safety and whether something's inductive using these automated theorem provers for logical satisfiability and validity. And over the last 20 years, we've seen huge progress in this area. And Microsoft Research has been at the forefront of that. So these are called, there's various types of SAT solvers. We heard about SAT solvers yesterday, and we're going to hear more about SAT solvers later. There's also something called satisfiability modulo theory. You want to reason about logical propositions with conjunctions and disjunctions, but you also want to reason about arithmetic, and you want to reason about bit vectors or sequences or sets or even strings, right? So there's been a huge amount of progress in automated theorem provers, to the extent that now for automated deduction we can take the notion of a system specification, say a protocol, an implementation described by initial set of states in a transition relation. We can take a safety property, which is not the bad set of states, and some loop invariant, and we can feed these into a theorem prover and get out answers. And of course, again, the answers might be positive. Yes, you have a proof. Negative, here's a counterexample to the proof, like a test that shows you that you don't meet the property, or because we're still perhaps dealing with undecidability, I don't know. So we have a three-valued response. And so over the last, well, really since 2006, at Microsoft Research, we've been working on something called Z3. How many have used Z3 here in their work? Okay, very good. Lovely. If you haven't yet, you'll learn a little bit more about it. It's an automated theorem prover in the satisfiability modular theories class, although it does actually quite a bit more now. And it's open source. It's won numerous competitions. It's been used in Microsoft for many of our software verification and testing tools, and it's been used outside as well now. It's open source under MIT license, so it's available for both commercial commercial use and research use. And here you see some of the theories that it reasons over, which I mentioned before. Reduction to logic. So what does this really look like in practice? So here's a little C# program. It takes an integer that's a assigned 32-bit value, and it does some manipulation. It copies that value to res. It does some bit twiddling on that, and it throws an exception if some condition is met. So is there a value of x that throws an exception? Well, you can sit down and work this out on paper for yourself, or you can, compile it using one of many tools to essentially a format, which is essentially reducing that program to a series of assertions about the bit vectors. It's encoding the semantics of each statement, if you will. I won't go into it. You feed it to Z3, and Z3 says, yep, here's your value. So in this case, we're asking Z3, does there exist an input X such that this program throws an exception? And if you want to see that in action, Z3 is available if you just want to play and learn about it. It's available on the web under a tool we've created called riseforfun.com, a service. And so there's that model, and I can just ask Z3 right there. It does give me the answer in hexadecimal, but you can do the conversion to yourself to decimal. There's a whole tutorial here as well. You can learn more about this if you go just to riseforfun.com/Z3. Oh, there it is. There's a big button. Tutorial. So this will take you through. You don't have to download Z3 or install it. It'll take you through. What Z3 is. Okay. Now Z3 has language bindings. You don't have to access it through the web. It has Python, C++, Java, .NET. And what does Z3 really do? It deals with some really hard problems, like SAT. The easiest problem Z3 deals with is NP complete. Right, and so the interesting thing here, and this is a whole research area which is fascinating to explore, is really the tension between greater expressiveness in the logic as you go up the stack and greater automation as you sort of go down. And so there's this real tension in proving and in dealing with different types of programs between what's the expressiveness of the logic you're reasoning with or using, and what's the amount of automation you can get from the theorem prover. So there's a huge amount of work. It's a very fascinating research area, and there have been theoretic undecidability results or complexity results that stand in the way sometimes, but there's also incredible engineering, especially at the SAT solver level. There's structure in the problems, algorithmic advances, the SAT competitions we heard about yesterday. So if you look at what's inside Z3 now, it's pretty incredible. There's a SAT solver, there's CutSat, there's quantified bit vectors, there's the existential reals, there's data log, so we can do constrained horn clause solving. There's effectively propositional logic, and there's a whole, it's not just SMT, there's a whole set of solvers inside Z3, and there's a whole set of tools on the upper left that are making use of it. Some of these are verification tools, some of them are model-based testing, some of them are C analysis, some of them are program proving. So this has really been, I think, 2 decades of substantial progress in formal methods. And it's not all about automated theorem provers. There's been a lot of use of interactive theorem proving, model checking, program analysis, a lot of advances in these 3 core areas of formal reasoning, and better tools. So I don't know if you're aware of CompCert. This is a verified realistic C compiler done at INRIA by Xavier Leroy and his team. There are also examples of fully verified small OS kernels. And more you see people around outside of core formal methods who are using formal tools to build verified systems. And there's work at MIT, Princeton, all over the world. So I think really over the last couple of decades, we've seen substantial progress. And I would say a lot of that is on the tooling side, better tools, but also of course, we have, and you'll see that a little later, we have a lot more big iron to throw at these problems as well. All right. Okay, so that is pretty much my overview. Oh, there's one more thing. I had 4 things to tell you about. Okay, let's see if we read. ULIT to SLA, bugs matter, formal methods matter. Oh, open source. So when I joined Microsoft, it was this closed source, and wow, have times changed, and it's great for research. I think it's great for industry. If you didn't see recently, I'll just let that quote. I won't even say more about it. But the browser wars, as we know them, are a thing of the past, right? It's quite amazing. Microsoft actively contributes to and uses open source. The tools that I present in this talk are open source, or you can find open source equivalents if the one I show you isn't open source. Z3 is our prime example, but a number of our tools that use Z3, in particular a lot of the verification tools, are all open source. And I think this is great for our community. It's great for the quality of our programs, because everyone will be contributing to open source as well as using open source. We want to make sure that all the code we're sharing and using is really of high quality. Okay, so that's the introduction. Wow, 10:34, so half hour, almost on the dot. Any questions? I want to take a little break. Yeah. Oh, okay, so the question is Z3 applicable only to software? And the answer is no. Z3 doesn't know anything about software. It knows just about logical formulas. So you have a problem like it's a scheduling problem. Z3 has some optimization algorithms in it. You can use Z3 for that. So yeah, no, Z3 has been used in modeling biological systems. I mean, this notion of reduction to logic is very powerful and is not in any way constrained to software. It's just that the major use of Z3 in Microsoft is for software analysis, and that's primarily what I'm talking about. But you can go out and find many other uses. Yeah.
I checked out Z3 before, and I found it quite interesting, and I saw that it has like improved quite a lot from the last time I saw it.
Mm-hmm.
But I have a question, like how scalable is it right now? Like at the moment, like do you guys use it for all the Windows drivers?
So the question is about scalability of the theorem prover, and the answer is it just depends. I mean, the theorem prover itself, I'll show you there's ways to parallel. So if you mean scale out, there's a whole research agenda about that. But yeah, fundamentally, you're dealing with, in the easiest case, NP complete. So the answer is no. You will always find cases of formulas which it'll just blow up, even for small formulas. So in no way, is it best of class? Yes, but doesn't mean you can throw any formula at it and you just sort of turn a knob and things will magically scale up. No, it's very, it's very hard and in fact unpredictable because fundamentally we haven't really come to grips with SAT. Right? We don't know exactly, right? There's all these heuristics. So fundamentally, there's a real unpredictability in using theorem provers, which is like I do a little tweak to my formula and all of a sudden something that was verified, in 5 seconds times out. And so this is actually, I think it's much, and there's a whole research effort Ken McMillan in my group is doing is about if you try to reduce your problem to decidable theories for which, you have a decision procedure, then maybe you can say something about predictability, but scalability certainly not so much.
Yeah, like other than the NP complete. But like
No. But you can't say other than NP complete. You're fundamentally in like a very hard space. So I don't really know otherwise. So how would you? Yeah.
What I meant is
Yeah.
how much is it used internally?
It's used all over the place. Like every one of our tools that does any symbolic execution uses Z3. There are people, look, if you have a very specific domain, you can go and do a decision procedure or some algorithm heuristic for that domain and beat Z3. But if you don't want to be bothered, you use Z3, right? Because Z3 is good enough for so many applications. It's been put under a lot of pressure by all these different types of tools. So that's a different question than scalability. I think that's a question about, yeah, I mean, yes, Z3 gets used a lot because fundamentally it's been hardened, it's been tested, it's been proven, it's been put through the mill, and that's worth a lot. It's a library that's, you know, it's sort of like, yeah, it's sort of been proven, and yeah, a lot of people just use it because they want the right tool for the right job. Maybe they'll come up next year with a tool that for their particular problem is, you know, is much better. Okay, one more question, then I should move on.
So what happened to functionality in the story from EULA to SLA? EULA, a big part of that was disclaiming liability for problems with functionality, but
Right.
the things you said about SLAs didn't really say much about it. Or anything.
Yeah, that's true. The functionality is still, yeah.
Liability.
Well, okay, I haven't read the whole SLA. There's a whole bunch in there about compute and availability. I don't know what the SLA says on other parts. Certainly around functionality, I think I would guess it doesn't have as much to say about things as it does about availability. Availability is sort of number one. And then and I'm only guessing right now that there are SLAs on other things like data protection, but I don't know for sure. Yeah. Okay, so let's move on and talk about some of these formal methods and tools. And I've oriented this towards distributed systems. Some of it might be a little bit more of a reach. We're going to start sort of at the bottom here with network verification and go up the stack. And the stack is sort of ordered by logical expressiveness. So at the bottom, we're just going to use bit vectors and SAT solvers. And everything is very automated. And as we go to the top, where we get to TLA, we have just set theory up there. And we have a model checker, but we have an incredibly expressive logic. Okay, so really all these tools and these problems they address, it's really about, I'd say, four things. It's about better verifying of our systems, testing, better ways to program them, and as Leslie likes to say, better thinking. Because if I can express myself and then debug my expression of intent, my specification, I can do better thinking. And the thing that ties them all together is logic. Like all these tools, whether they're doing low-level verification of code or new programming models with advanced type checkers or the high-level specification, they're all reducing problems of correctness and debugging to logic. Not all of them use Z3, but almost all of them do. Okay. So let's start with network verification. This is a very hot area, and Nikolai Bjorna is one of the leaders. He's in MSR, and he's been working with Kartik, who is an engineer in Azure. So Nikolai likes to talk about the masters of complexity. So in the upper left here, you have this cloud explosion. So you see this incredible growth of the cloud. Each data center, think about how many routers are in that data center that have to be configured. And in the upper right, these arcane ways that you have to program these routers. I mean, it's very low level. This is like machine language assembly language. And so the people who keep this cloud growing, Nikolai terms them masters of complexity. And so what he would like to do, and the idea of a network verification, is that we would like to deal with the cloud explosion and all the complexity that comes in keeping the cloud up and running by logic and good software engineering. So he has a proposal to use tooling as well as monitoring at scale to basically keep the system on the straight and narrow. So again, we're going to have a specification of what it means to be a good data center. And then as people change the configuration of the actual data center, we're going to actively check to make sure the data center is still a good data center. So what does it mean to be a good data center? Okay, well, we have to talk about these network policies a little bit. So several devices. Within a data center, there will be many devices from different vendors using different formats, firewalls, routers, filters. And then at the high level, we want people to come in and use this big machine, but we need to keep them separated from one another. We have administrators who are doing management services. We have users and tenants who are deploying virtual machines. And we have policies to keep everything good, right? And so mostly manual effort in these low-level configuration files, the data says that the number of human errors in configurations is greater than 4, leading to DOS-style outages, denial of service. So things that happen in the data center that look like a denial of service are caused 4 times more by human error in configurations than actual denial of service. So it's a big problem, right? This masters of complexity still get it wrong. Because again, entropy, bugs will just happen, right? Even with experts, they will have a bad day, they will make mistakes. And so if you look at this, 74% of the human errors by activity are from configuration changes. If you take a software or hardware update, 13% of the errors in configuration errors come out of that, and then various ways of when you're expanding or doing a setup. So the idea here is really to bring verification. On the left-hand side, we have the reality of the system. For example, in a router, you have forwarding information, or you have, in other places, access control lists. And this real data is being churned because the data center is growing, because somebody wants to put a new policy into account. We have intent, and so we actually have now in Azure contracts that are independent of the implementation, that are derived from the topology and architecture, and basically state various policies. This is called a network graph service. The third part is we are continually validating the reality against the intent and giving feedback. And Z3 is an integral part of this. So just to give you an example, here are 2 very simple contracts. If I'm running a service, I need to do DNS lookup. So I'm a tenant. I want to access, it should be the case that DNS ports on DNS servers are accessible from tenant devices over both TCP and UDP. That's reasonable. The other contract is also reasonable, is a deny. Within Azure, there are management devices. That is the devices that people in Microsoft use to keep Azure up. The SSH ports on the management devices should not be accessible from the tenants, right? Normal users of Azure shouldn't get to go in and manage Azure and bring it up and down, right? Okay, so those are just some very simple policies. So what Nikolai and Kartik have done is they've created essentially translators from the low-level formats for all the routers and the different devices that you see on the left here into precise semantics as bit vector formulas. And there's basically, at the router level, there's basically very simple rules. Either you want to allow traffic from some source IP range to some destination IP range for some particular protocol, or you want to deny it. So the contracts get much more expressive than this, but what is an IP address? That's just a bit vector, right? And then what are these constraints? These are just range checks over bit vectors. So the logic here is very simple. We can automatically derive the bit vector inequalities, from the configuration files, and these are decidable, totally solvable by reduction to SAT. So we get this is the reality. We have a combining semantics that says essentially you don't want any of the deny traffic to take place, but you want the allow traffic to take place. And then we have a semantic diff using Z3, which is essentially comparing the implementation against the spec and then pointing out differences. Okay, so I might, and what might be a bad example, like I might allow some traffic that should be denied, or I should deny some traffic that should be allowed. Now the way SAT solvers work and the way Z3 works is whenever they find a counterexample, they produce a model, which is actually a concrete value. And you saw that with the C# program, it came up with a value. But here you're talking about IP address ranges, so what does a counterexample look like? Well, it could be like hundreds of IP addresses it could be a very large number of values. So what they've done in this particular application is they take, say, the specification on the right-hand side, the implementation on the left, and they synthesize back a readable IP address range. So instead of enumerating all the counterexamples, they put it back in the language of the configuration routers, which is there's generally some shorthand for denoting an IP address range. So there's some a cute little algorithm to basically take to find the best expression that captures all the counterexamples all the counter examples, rather than enumerating them all. So the idea with this tool then is to actually put it in production, and this is what's happened. Sekuru is in this monitoring framework called WA netmon, and it is run there, according to Nikolai, there's about 40,000 access control list checks per month. Each check is taking at most 200 milliseconds, and they're finding about 20 bugs a month, mostly when they're building out new data centers, right? But this tool also actively helps if they want to reconfigure the routers or do something. So you can make a change, and before you deploy it, you can do the queries to Z3. But also some changes are being made automatically, so the tool is actually also run actively inside the data center as part of a monitoring suite as well. So this is just the tip of the iceberg for network verification. A network verification at the router level is just talking about traffic, on a particular port from some source to destination. But once you really start thinking about the networks, you think about routes, you think about things like BGP, you think about all these higher level policies. So the idea of keeping a data center up and running isn't just about the low level routing, it's also about all the other things you need to do. And Nikolai and the colleagues are actively doing that. If you want an example though, if you want to play with code yourself, Andrew Helwer in Azure has written a firewall checker and made the code available for that does very much what Sekuru does. And so that's an open source example of what Sekuru does. Yeah.
How do you figure out this formula that says it captures all the conflicts?
That is where I would say please talk to Nikolai and read the paper, because I do not know. This is where I'm pointing to the good work of others. I'm not exactly sure about that. That's a very good question. Okay, so we'll take that offline because I don't know, and I have many other things to tell you about. So let's go up the stack. Oh.
You mentioned that certain percentage errors were caused by software updates. You mentioned that certain percentage errors were caused by software updates.
Oh, software updates. Yeah, that's right.
So would that figure in this chain or not? That's an independent chain. Because I don't see how you could.
Yeah, no, I think Sekuru is not gonna address that. Yeah. I think with formal methods, you always need something else. So I think it's a mistake we need a toolbox, a wide-ranging toolbox, right? And formal methods and the sort of checking, I'm telling you, we can address. We know we can carve off a big chunk, but there's always more bugs that are sort of outside our spec, right?
So these 20 bugs that you get a month or a week, you find these 20. You said you find about 20 bugs a month.
Yeah, but that's mainly because of new data center expansion, according to Nikolai.
And I guess I'm wondering how effective is the information that you get from those bugs in terms of people fixing the bugs?
Oh, I understand from Nikolai, these are fixed right away. Like, no, there's no false alarms here. Like, we're not in undecidability space or anything. Like, these really matter, and these things get fixed.
What I meant is that sometimes when you find a bug, expressing the bug in a way that people understand how to.
Yeah, and I think that's where it comes back to this dashboard, which I really can't read, but fundamentally it's integrated with a tool that people use already for doing network monitoring, and this is where Kartik comes in. There's a whole set of tools, and they work with the users, the DevOps and the people in the data centers use these tools. So my understanding is, this is tightly integrated into the tool chain of how the operators are working. And in fact, a lot of the work that we do that we don't publish about is exactly this, right? It's about the last mile, like actually presenting the bug in a way that people can take action on it, and it's a very good question. So let's move up the stack. We're going to talk about testing next of programs in this case. And this is something that's a long story that's been going on for a while, based on symbolic execution of paths, like I showed you in the C# program. And we now actually have a product, a service called Microsoft Security Risk Detection that is based on really about 15 years of research. And well, again, the original ideas go back to the 60s and 70s, but now they're deployed not only inside Microsoft like Sekuru, but this service is available for anyone to use. So the idea here is this blue bubble at the bottom is some parser written in C and C++. And you would not believe how many different file formats there are that Windows supports and Office supports. Or you go out to the world and any SAP, any company or whatever, and you say, how many file formats do you have? Oh, lots of them. And some of them are text-based, some of them are XML. A lot are binary formats, and the parsers are written in C because C is pretty nice for dealing with binary, at least it was. It still is. So you have these parsers, and you have buffer overflows or type errors, and now you're making that parser available over a trust boundary. So you have a surface area, you have an attack vector, which is like, okay, can I create an image file and give it to your image parser that will cause a buffer overflow, and then embedded in the image is some executable code. Can I get in there? So I've got data flow moving across the web, moving from an untrusted source through a trust boundary to some entry point, eventually gets to a C function, a binary blob. The C program was written by hand. If I have a security bug, now I have a potential exploit. This leads us to potentially a 0-day, but there's many steps in the way. But this is the first point. And when we're making more of our code available on the web, more of these sort of parsers and data formats might be accessible just over the network. So the idea of input fuzzing goes back to a long way. Black box fuzzing just says throw binary streams at your parser and see what breaks. And there was a paper out of Wisconsin, my alma mater, with Brian Sill and Bart Miller. It was in the early 90s. That just did this with Unix utilities, and about every 5 years somebody repeats that experiment, and there are still bugs in the Unix utilities if you just throw random byte streams at them. But you can do better than that. So if you give an initial input good, the good string, to this top function that takes 4 characters, well, hidden in this code is a crash, and that crash only happens on a particular bad input. But for the good input, all of these conditionals evaluate false, right? And so we don't crash. But what we can do is we can symbolically execute this path while it's being dynamically executed, collect up the set of constraints. And what are these constraints? They're constraints over an input of 4 characters. What's that? Oh, it's a bit vector. Okay, so essentially a C program reading a fixed array of bytes essentially reduces questions of path feasibility or execution reduced to bit vector problem. Now, it's not entirely true. You can start to get other sort of logics in here depending on how open the program is, and you might have some global pointers here. You might have other things that become symbolic. But essentially what you're doing is you're not verifying your program, you're just choosing paths, and each path in some sense is a constraint over the input. So we see that if we take the good path, we're on the blue side. These edges going off represent the conditionals evaluating true. And so what we can do is we can take the last conditional and flip it to say, okay, instead of the 4th character being not equal to the bang, we're going to make it equal to bang. And then we present Z3 with a constraint that says, find me an input that satisfies the 4 conditionals, the first 3 in blue here, and the 4th in teal or whatever that is. And in fact, this just gets submitted to Z3, and it comes up with goo bang. And now that goes in we can do that for each of the branches in that original path. So this is sort of a breadth first strategy. We have one path. We have all the conditionals that go off the path. For each of the conditionals, we can flip it, and we can get a new input. And that's sort of generation 1. And then we can go and do generation 2, generation 3, and eventually, in this particular search strategy, we get to the bad string, bad exclamation mark, and we get the crash. There are many other search strategies, but the basic idea is I start with some random seeds, or some input files that already exist for the program. I execute the paths, and then I collect some coverage and try to find new paths, and then generate new inputs. And that's essentially what this diagram shows. So I start with some input here. I run the program, check for crashes, get some code coverage. I could use the code coverage to tell me, oh, here's some part of the code that's uncovered. So there are many different ways to do exploration, search-based testing we heard about yesterday. But the idea is you're going to generate a new path via some search strategy, and then ask Z3, is there an input that goes along that path? You get new inputs, they come back. And this whole idea of fuzzing, whether it's black box or white box, is part of the SDL. Remember the SDL? Okay, so the security definition lifecycle that's been in place now since early 2000s says that you must perform fuzz testing as part of verification. But in the limit for a program with no loops, you could exhaustively, if you had enough time, explore all the paths. But even for an acyclic program, you could have an exponential number of paths. And this is what has been going on in Microsoft since the mid-2000s. So Sage has been applied to many, many parsers in Windows and Office. And here are some of the bugs found from 2006 to 2009. On the left-hand side, this is the black box fuzzing and regression testing of the parsers. So it found some number of bugs, which I'm not allowed to tell you how many. And then there was some other way of testing that found this. And after those two techniques, which are the basic techniques, have been done, then this Sage came in, and it found basically a third of all total bugs. So that's pretty good. You know, after all the other fuzzing tools and all the other techniques have been tried, this notion of white box fuzzing came in and found hundreds of more bugs, and some of these could have led to things like zero day. So this is what Sage is, but it's been now encapsulated in a service, and so now this service we are making available, and it is an Azure service that uses Sage and other fuzzers, but you submit a job, a binary, and some input files, and you say, here's the function in the binary that I want you to fuzz, and now it parallelizes over many machines. So you say, you know, I want to do fuzz testing across so many VMs, or I want this number of tests generated. So what we do is we run Sage for you, essentially in the cloud, and scale out to a whole number of VMs, and then we bring all the results back and present them, pretty much like you saw with the netmon. So the idea here, though, is like people can submit their own binaries, and I think we have fuzzing for both Windows and Linux at this point. So this is very interesting. Dynamic symbolic execution, this idea of running your program and then collecting constraints. There's huge work around this. CLE is one of the best known, which is for real C programs or any program compiled through LLVM. I think the first international CLE workshop just took place. If you want to learn about dynamic symbolic execution, then I recommend you go to my little GitHub there, where I implemented a tiny little symbolic executor for Python using Z3. And that has a paper. And so if you just want to learn about the core ideas, I would recommend the second one. If you want to just apply it to like some C programs yourself, CLE is there as well. And let me just end this part by saying there's a lot more to say about fuzzing when you really start thinking about the cloud. What I've been telling you about with Sage is really fuzzing C programs. So a program that takes a binary blob and they may have errors. But today, when we talk about cloud services interacting, they're not calling C functions. They're not calling another service via C function. They're working through REST, right? They're working through higher level APIs. But the same principle applies here. They're doing some sanity checking. There's a whole sort of protocol there, and there's a whole opportunity to do intelligent fuzzing at the API level of cloud services. So Patrice Gaffra, who is behind Sage and the work there, has been going on to think about how do you do Sage-like things, but now it's a real black box, because you are really fuzzing a service for which you can't go and look at the internal code. But can you do smarter things? And so they have a preprint available about that. So this whole area of fuzzing I've shown you at the level of C, network fuzzing, cloud-based fuzzing, APIs. This is sort of the next step that we're investigating. As more and more our programs are combinations of services or microservices communicating with one another, we have these interfaces. There's an opportunity to come, well, there's an opportunity for attackers, but there's also an opportunity for us to get ahead and look at fuzzing at the interface level. Yeah.
Can you tell us a little bit about the environment modeling in Sage? How is it handled? Not just the physical environment.
Yeah, so the environment modeling problem. So in Sage, you really have to have a closed system. That is fundamentally this function that reads the binary blob. That's all it does, right? If this thing goes off and makes network calls, or Sage will, you may have non-determinism. So Sage will handle that, but your results may vary. So the issue is, what is your C function doing? What's it dependent on? If your C function is purely dependent on that binary input, the 4 characters, it's deterministic, then Sage can give you a guarantee that given enough time, it will explore all the paths. But if there's non-determinism in the function, if it calls some, if it goes get time of day and then does some check, right? So Sage doesn't have particular ways of dealing with that. So you fundamentally, as the person providing the test, have to think about which function is you want to. And there's a whole another research area around deterministic execution, like making programs that do call into the environment, making them deterministic. Sage isn't really addressing that.
Libraries may need to be manual or effective.
Yeah, right. So again, Sage is working at the binary level. So the assumption is you have the complete code. Of course, it's not going into the kernel. So yes, at some point there's a transition out of proc, and Sage does have some built-in models. But again, for its particular domain of file fuzzing, that's a very small set. So the environment problem is not as big a problem as it was with static driver verifier, where basically I have a device driver and it can call back to the kernel to get all sorts of services, and it's the footprint is huge, the API footprint. So here with Sage, it's much more about this binary parsing, and so yes, it could call all other things, but what Sage is used for is it's more. Yeah, exactly. The input byte stream is the environment for the most part. Yeah.
One challenge of symbolic execution is that it's hard to scale it well. So how
It uses Azure. So fundamentally, as I understand what they do with Sage is they have different inputs and they start running it over different machines. So it's path-based, so it's exponential, it's unbounded actually. It scales perfectly well, actually. I mean, the problem is there's just so many paths, right? So fundamentally, it's sort of it's easier than SAT solving. I mean, SAT solving, you have the problem of learned lemmas and things like that. Sage, in some sense, has learned inputs. So if one machine learns an input that's sort of isomorphic to some other input, I guess. But really, it's sort of embarrassingly parallel, but the problem is the search space is huge. So, I mean, it's no different than sort of model checking and stateless model checking in that sense. I mean, it's parallelizable, but yeah, there are limits to all these things. I don't know that Sage has any secret sauce there. Yeah, I mean, and again, don't ask to like, okay, so for example, like looking at a JPEG, like fuzzing a JPEG parser as opposed to fuzzing Word. Yeah, so we've done that, right? It's much easier to do JPEG because that format's a lot simpler. So yeah, you give me a program that has many more decisions and many more branches. There are ways to deal with that. I mean, fundamentally, you could try to do snapshotting at intermediate points and then do internal fuzzing. I mean, there's a whole research you could do, but it's sort of, I mean, it's good enough. I think fundamentally we've done a lot of tuning. So I guess I would say just read the papers. I mean, it's good enough to put a tool out and we get users and it scales well enough. We haven't really like, will people, again, like with SAT, will people come up with things on which it will bomb or, run out of time? Absolutely. I think it's just inherent in the problem. Okay, let's move up the stack to programming. So what I've told you so far is dealing with essentially the world as it is, which is these are routers, these are how they're programmed. This is parsers, these are C programs that implement the parsers, and we just want to find bugs in them. But what if we actually got to invent a new language and did it a little better? So remember that little problem we had with OpenSSL? So people had been thinking about crypto and how to make it correct before OpenSSL came about, and some of those people are in Microsoft Research. So they started something a couple years ago called Project Everest, and it's a mountain. It's a very, very long climb. It's a multi-year project to essentially have a verified replacement for HTTPS. And it's not about verifying everything, like we're not trying to verify TCP/IP. We're just there, but there's this important module there that has a bunch of submodules, and we know through history we've seen lots of bugs. And Heartbleed is one example. And what we'd like to do is not only have a replacement that's verified, but that the performance of that generated code is decent, which means we have to generate real C code and in a way that it can be compiled and accepted into, say, a real browser. So it's not just about creating some model of HTTPS and running it off on the side and doing some experiments. It's actually having a performant piece of C code in the end that can be incorporated in existing, say, existing browser. So this is the idea of Project Everest, and Everest uses three main technologies. At the top is a new language called F*, which is a functional language designed based on F#, and it uses Z3 because F* has a very rich specification language that you can reason not just about the types, but about constraints on the types, the fact that you might have integers and inequalities and bit vectors, and all these logical constraints are being discharged by Z3. And in this talk, I'm only just going to focus on the part of Everest that's looking at crypto. So this is a base camp. Before you can climb to the peak, you need to reach a base camp. I can't remember the names. There's several of them, right? I can't remember if that's base camp 1 there, probably. So if you want to do HTTPS, you have to do crypto. And in order to do that, you need a variety of different cryptography primitives and algorithms implemented, and these need to be, implemented very efficiently because you're using this crypto to secure all your data being sent. And fundamentally, there's a lot of variability because of the different types of crypto you have and their requirements. So the efficient implementation, for example, of Poly 1305, which uses a prime field with P being this prime, needs 130 bits to represent a number, but there's various requirements on the big nums and the way you use bits in each word. So on x86, you're using 5 32-bit words to represent the prime, but only 26 bits in each word. And on 64 bits, it's different. And with this other cryptography primitive, it's a different prime, and you're using 5 64-bit words. So OpenSSL, if you look into it, because of all these different cryptography primitives, it has 12 unverified big num libraries. So just representing larger numbers than fit in a word takes, you have already 12 different options to choose from. So let's go down and just say, okay, first things first, let's have generic efficient big num libraries. So what they've done as a starting point, and they've done a lot more, is to have big num code that can be shared between these different cryptographic algorithms, primitives, which all use different fields. And the idea is to write the big num code once, verify it once, but then through genericity and parameterization, since it's a module, extract it to efficient C code for the different uses. So I'm not going to show you or read to you what this spec is, other than to point out that the logic here is not just bit vectors anymore. So when you see requires here in this poly 1305, okay, first of all, we have a bunch of parameters, right, that are typed, strongly typed. Okay, we actually have some dependent types. And then we have a precondition and a postcondition. And these preconditions actually have quantifiers. So it's shown here as a lambda, but it's basically saying for all H, some message in H and key in H and tag in H. So now our logic has exploded from just bit vectors with no quantifiers up to actually a very rich logic that has types, dependent types, as well as quantifiers, because we need to talk about collections, we need to talk about all the bytes in a particular buffer and properties of those bytes. So essentially the mathematical spec in the upper square here is saying that we want this function to compute a polynomial in this particular field. It stores the result in tag, and it doesn't do anything else. Like it doesn't overrun a buffer. It doesn't do anything else but points 1 and 2. And a lot of verification problems are this problem of it, and it doesn't do anything else is a big problem. Yeah.
The fact that it doesn't overrun the buffer, where is it encoded? Because it seems like it's basic safety that this core style specification requires of course, but it's not there explicitly.
Yeah, it's got to be somewhere else. You're going to have to ask them. Right. So I would say, yeah, again, if I could actually read this myself, it should have something to do with this disjoint tag and the length here, but the devil's in the details. This is the C code that we get out from the whole compiler chain, and this is what the compiler chain looks like. So type checking is actually a combination of classical type checking plus calls to Z3. Because we need to reason about, say, the length of a buffer and constraints on that buffer and an index into the buffer. We're reasoning about arithmetic constraints. So the F-star compiler uses Z3, then it reduces its program to a smaller language. This is classic compiler. And then it uses a second compiler called Kremlin that generates readable C code. So this is quite important. Because remember, the goal here eventually is to go to C programmers and say, we've done all this verification work, okay, and what are we going to show them? Well, if we show them a binary, they can't read it. So we should show them in a language that they read, and it should be well formatted and stylistically pleasant. So this a lot of the work in Kremlin is optimization work, inlining efficiency, making the higher order functional language, a subset of it, efficiently realizable in C, which is a whole big research area, but then to output it so that we can do code review. Because remember again, formal methods by itself, we need to, if we want to go the last mile and work with industrial partners, they have expectations like, show me your code, let's do a code review, let me do a set of tests on it. So that's been a lot of work in the tool chain. And the results here on the left show you for various algorithms, the specs, the number of lines of F-star specs, the code and the proofs together, the number of lines there. So this is not just the code in F-star or low star, which is a subset of F-star, but actually the inductive invariance and everything, the pre and post conditions. This is the amount of C code we get out in the end. And this is the time in seconds to do verification. So there's definitely overhead. It's quite reasonable in terms of, I think, the produced code. But also, it's about efficiency. So for example, here we're looking at the efficiency of the primitives in Hacklestar, which is this whole library that we've created in F-star, compared to OpenSSL. So I think the one they wanted me to point out here was that for curve 25519, we're getting it's the number of cycles per elliptic curve computation, and the code here for 64 by 64-bit multiplications verified is about half the number of cycles per computation than in OpenSSL. So we're enabling these algorithms to be written, proved correct, but through the tool chain, we're getting efficient C code. So I think this is actually a big change in the last 20 years from formal methods in the 20th century, where we did a lot of verified work, but the result was a Lisp program or something that took a lot of time to run and could be used in particular situations, but you wouldn't imagine putting it into a browser, right? But that's what's exactly happened with a number of the primitives that have come out of the Everest project. So Firefox is shipping with some of the C code that has gone through this entire process that I've shown you. So it was written in F star with pre and post conditions. It was proved correct using Z3. And the C code extracted met the demands of the Mozilla engineers and was incorporated into their security engine that's inside Firefox. And we're not the only ones doing this sort of work. There's work that going on at MIT on crypto that is also seeing similar adoption. So I think this is a big difference from the 20th century in terms of formal methods. Not only are we going to prove the program correct, but extract efficient performant code. And so just like C compilers sort of eventually got rid of people writing in assembly, we hope that for certain very low-level domains that are key, like crypto, the future will be that people will rely on tool chains like this rather than hacking on the C code to try and get the crypto right. Because for these sort of components, it's very critical. They're a critical part of the global economy. So that Everest project is going on. They are actually working. They've worked on formalizing TLS 1.3. They're doing proofs of correctness there, extraction of protocols. So it's not just about, I don't want to give you the idea, it's just about the crypto. It's also about the rest of the stack. Yeah.
So has the compiled binary gone through any independent testing? Because you are trusting like a chain of compilers in a way and
Yeah.
bugs in the spec. So any experience of finding bugs in the ones that have been fully verified?
Not to date. I mean, yes, it goes through a variety of compilers. So the trusted computing base here is quite large, right? Mozilla uses, I don't know, I suppose they use Clang or GCC, I don't know for sure. Probably not ComCert, right? Yeah. So I'm sorry, I just don't know. Yeah, but they wouldn't take the resulting code and put it in Firefox, I'm pretty sure. They could.
It's not mature yet. It's not that mature.
ComCert does not have all the optimizations that I think they would want. Yeah, yeah. For people are paying for ComCert. There are people who want that compiler for their uses. I think for this particular one, they might not. But yeah. There's lots of Project Everest and all the tooling, the language, the compilers, the assets that have been proved correct. Everything is open source. So this is completely open and available for inspection, as it should be with the CERTA project. Wow. I've actually got time left. I didn't realize that. Any other questions on that part? Okay, I didn't think I was going to get to TLA. How many people know who Leslie Lamport is? Okay, that's good. That's good. So Leslie Lamport, in some sense, is the father or grandfather, no, he's the father, of distributed computing. I mean, you heard a lot about his work from Valerie, right? She kept saying, Leslie said, I told Leslie, about the Byzantine consensus, and he said, no, nobody wants Byzantine consensus. Anyway, so Leslie's thought over the years very deeply about what is concurrency, what is consensus. He's created a number of the key algorithms that the distributed systems are built upon. He's received the Turing Award for that. And along the way, he did other things. You might have heard of LaTeX. Does anybody here use LaTeX? Yeah. Leslie wrote it. Well, it's probably been rewritten sometimes, but Leslie created it. I mean, and he also created this thing called TLA, which is about 20 years old now. And his idea is a very good idea. It's like, well, before I go and even write a program, I have something in mind, an algorithm or a system. Why don't I do a high-level design? And furthermore, math is a perfectly great language for doing design in, and people learn math. Why do we need to invent a new programming language? So Leslie has created TLA and there are books and users, and there are tools for model checking. But this language is incredibly expressive. I mean, it's essentially set theory. So you can express, you can be very expressive. You can express the set of all sets that do not include themselves. You can write complete nonsense in it. But you can also write, you can design algorithms at a very high level. And so it's not a programming language, it's a design language. It really is pure logic. There is something called +cal, which is like a pseudocode. So you can pretend you're writing in an imperative language, but really it's pure math and logic. And there's an IDE and a whole toolbox. And if you haven't seen it, Amazon and people who are doing distributed computing, these are experts. Remember the masters of complexity? So the masters of complexity, when they wanted to design a new version of Paxos or one of Leslie's algorithms that doesn't quite work for their situation, these experts are using Leslie's tooling to debug their new design before they go to code, because they realize that this area of distributed systems and these protocols have gotten so complex that even experts make mistakes, right? So they write down their designs and they debug them using formal methods. And so this is a great story. And I think it also speaks to the fact that formal methods is not about getting everybody to write specifications in all their programs. It's about the right tool for the right job. And when you have a domain that's super complex and difficult to think about, you want tools that help you do that job. Now, if that has to do with writing C programs that parse binary, that's one type of tool you want. But if it's designing a new version of consensus, there's another tool, and TLA is that tool. And there are other tools we're working on as well. So I think it's really interesting to see that you have these experts who wrote this paper, who are engineers at Amazon, who basically said, formal methods finds bugs that we can't find through any other technique we know of, because these distributed systems, how do you test them once you deploy them? It's very difficult. It's a very complex system. It's not just a simple sequential program like the C program reading from a binary blob, right? They found, these are quotes from the paper, they found that the formal methods are feasible for mainstream software development and give good return on investment. I don't know about the mainstream. I'm thinking they're pretty specialized in what they do, but it'd be nice if it were mainstream one day. But I think that the third one is really interesting, that they are using them routinely at Amazon in the design of complex real-world software, including their services. So when they have hard problems, they're looking to TLA+. And this is a quote that I think Chris sent Leslie. It's on one of Leslie's pages that's worth reading. TLA+ is the most valuable thing I've learned in my professional career. Changed how I work, giving me an immensely powerful tool to find subtle flaws in designs. So they're using this at design time, right? And this is happening across the industry. Microsoft has also been using TLA. There's other folks using different languages at different companies. But I think the idea that when you're working in a really complex domain, you want aids to help you debug your design is really critical. So this is what I'd like to end with. I think you've seen through this work these different types of tools that we have completely automated at the bottom for this very, very narrow specialized problem of configuring the routers in the data center, all the way up to really thinking about the protocols that at the high level control the data and the processes in the data center. Logic is the foundation for all of it. But really what makes the logic come alive are the tools and the approaches, whether they're model checking or theorem proving. They're really trying to automate the tedium but also show you where you might be surprised, right? That you've considered cases A, B, C, but did you know also there was a case D, you didn't consider. These tools are good at explicating this. So I think, yes, so that's pretty much the talk. I did want to give a shout out to all the people who are behind the technology I've shown you today, and there are dots because there are many more in the product groups, but these are the core people who've been doing the research and the development of the technology. So with that, I will conclude.